All right, I want to show you something called the accumulation function. Before we get started, I want to remind you of a couple things about the definite integral. We know that the definite integral is the area bound by the function and the x-axis. If we're going to evaluate the definite integral from 0 to 2 of f of t dt, that's going to be the area bound by f of t and the t-axis. So with the graph I have here, we can think of this as being our t-axis. The curve is f of t, and if we're going to go from 0 over to 2, then the definite integral is this area, 2.7. Now when we go from 2 over to 5, because this is below that t-axis, that means that that definite integral is going to be negative 7.3. So it is possible to have a negative area. The positive area would be above the x-axis or t-axis, and the negative area would be below it. So if we're going to go from 0 to 5 and find that area, we would take the integral from 0 to 2, which was 2.7, and add to it from 2 to 5 the negative 7.3. All right, so altogether, we have all this positive area on top, and then all this negative area on bottom. Some of that is going to cancel out and we'll be left over with more negative area. In fact, there will be 4.6 left over on the negative side. Now, let's evaluate the integral from 0 to x of cosine t dt for 4 different values of what x can be. Instead of starting from scratch and going from 0 to pi over 6 and then from 0 to pi over 4 and so on, what I'm going to do is I'm going to create this new function, f of x. Right? And that's going to be the integral from 0 to x of cosine t dt. And we know how to calculate that because the integral of cosine is going to be sine. And with the definite integral, we evaluate it from 0 to x. So we're going to plug in the x first, and we'll have sine of x. And then subtract off sine of 0. Well, the sine of 0 is 0. So when this all simplifies down, we have this function, big F of x is equal to the sine of x. Now, when I want to evaluate for these 4 different values, all I have to do is let x be first pi over 6. Okay? And so from my function here, that would be the sine of pi over 6, which is 1/2. And big F of pi over 4, that's the sine of pi over 4, which is root 2 over 2. Big F of pi over 3, sine of pi over 3, is square root 3 over 2. And f of pi over 2 would be the sine of pi over 2, which is just 1. Let's take a closer look at what we just did there. See, if we have big F of x being that definite integral from 0 to x, and we first found f of pi over 6, what we're doing is finding the area under the curve from 0 out to pi over 6. So we found this much area. Then, when we move to pi over 4, what we did is kind of took that endpoint and shifted it out to pi over 4. So we found this much area. We accumulated some more area. As we continued to pi over 3 and pi over 2, we kept kind of moving this endpoint out to pi over 3 and found this much area, and then all the way out to pi over 2 and found this much area. Okay. So as we let x move along, we just kept accumulating more and more area. That's why we call this the accumulation function. So where on the interval from 0 to 2 pi is f of x going to be the largest? Now remember, with big F of x, we're accumulating area. So we're starting when x is 0, right here. And then we're going to let x kind of move along. And as we kind of let that endpoint keep moving along and we start collecting more and more area, we go all the way to here, and all of this is going to be positive area. In fact, we saw that f of pi over 2 is 1. So the area of that is plus 1. As soon as we go beyond that pi over 2, then we're going to start adding on some negative area. So basically taking area away. And in fact, because of the symmetry of cosine, that we can go all the way out over to here, and this area is going to be -1 because it's all underneath the x-axis there. So we would know that big F of pi is going to be 0. As we continue along, we're going to continue to add more negative area. And so all of this would have that same -1 area. So f of 3 pi over 2 would be -1. Then the curve goes on the other side of the axis and we begin to add more positive areas. All right? And so when we get down to 2 pi, this area would be another +1. And so f of 2 pi is going to be the +1, -1, -1, now +1 again, and we're back at 0. So where does this thing have the largest value? Right here. All right, when all we've done is add positive areas and we haven't had any negative areas to counter any of it yet. Notice that that is also a 0 of the original y equals cosine of t. So let's talk about the velocity of a bike. Let's say it's measured in feet per minute and it's given by v of t is equal to 3t squared minus 2t. And we want to write the accumulation function. I'm just going to call it d of x. All right, it's got to be a function, so we need some functional notation. Just to get practice writing an accumulation function, it's going to be the integral of that v of t and we're going to start at 0 and then we go up to different values of x. I do want you to actually evaluate this definite integral. So we take the integral of 3t squared minus 2t, and that would be t cubed minus t squared, evaluated from 0 to x. So we plug x in, and we'll get x to the third minus x squared, and then subtract off when we plug 0 in, and that's 0. So our accumulation function is d of x is equal to x cubed minus x squared. So if we're going to evaluate d of x for a few different values, remember d of x was x cubed minus x squared. So really finding d of 0.5 is just plugging 0.5 in for x. So cubed minus 0.5 squared. And that'll leave us with -0.125. d of 1, plug in 1, and we'll get 0. d of 2, plug in 2, 2 cubed minus 2 squared is 4. So just some practice finding an accumulation function and evaluating it. If we want to find where d of x achieves its minimum, we don't graph d of x. What we want to do is actually graph the velocity function, because d of x was the integral of that velocity function. Okay? And our velocity function was 3t squared minus 2t. That means it's a parabola that opens up. It has a 0 at 0 and another one at 2/3. So the graph is going to look like this. where that one's at 0 and that one's at 2/3. We don't want to know where the velocity function achieves its minimum. That would just be down here at the vertex of that parabola. What we want to know is where does the accumulation function achieve its minimum. Right? And remember, the accumulation function is going to accumulate area as we move across. Right? And when we get to this 0, this would be the maximum amount of negative area that we could get. Right? So that's the maximum negative area. As soon as we go beyond that, then we're going to start to collect some positive area, right, which would cancel out some of that negative area that we found. So the minimum of d of x is the most negative area that it has. That's going to happen right here when x equals 2/3. Another area that gets looked over a lot when we're dealing with calculus is we focus so much on the mechanics of how derivatives and integrals work that we kind of forget about units. And I do want to think about units here in all this stuff that we've been talking about, especially in this last example where we're talking about the velocity of the bike. We were told that v of t is measured in feet per minute, right? Which would mean that time, we can assume, is measured in minutes. So what about x and d of t and d of x? Right? Well, thinking about what d of x is, right? D of x is the integral from 0 to x of v of t dt. Okay. So since x is one of our limits of integration, right, we would integrate v of t and then plug in 0 and x in for t. So that x has the same type of measurement as time does. And so this would also be measured in minutes. What about d of t? Well, if you think about the origins of the definite integral and those Riemann sums, we said that d of t came from the change in t, or the change in time. So a change in time is still a measurement of time, and so those units would be minutes as well. So what about d of x? What are going to be the units of d of x? Right? Well, when we break down what the definite integral is, the integral, the elongated s, we use an s because it's a sum. All right? The sum of all of these little rectangles. Velocity was measured in feet per minute, and the change in time was measured in minutes. So when we multiply these all out, we end up with feet, which means d of x is actually a measurement of distance.